Okay, so hopefully this way of recording works without me having to edit it into rotation. So, continuing where we left off with the exercises from section 1.3 in Dummett and Foot. We have exercise 9, which has 3 parts. Part A, oops, that's too big a marker. So part A is let sigma be the 12 cycle. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, sorry. And it asks us, well, okay, so for which positive integers is sigma to the I also a 12 cycle? So that's what part A asks us. Now this has multiple parts, right? So let's go to part B. What does part B ask us? Part B says, well, let tau be the 8 cycle. 1, 2, 3, 4, 5, 6, 7, 8. And for which positive integers I is tau to the I also on an 8 cycle. Let omega be the 14 cycle, so we can sort of see a pattern here, right? One, 2, 3, 4, right? We know where this is going. Wait to 14, for which positive integers I is omega I also a 14 cycle. So intuitively, how would we go about solving this, right? Well, if, say we had a cycle pi, we use the symbol pi, And we say that that if pi is an m cycle, then pi to the I breaks into GCD of m and I disjoint cycles, each of length m divided by the GCD of m and I. Thus, pi to the I is again an m cycle exactly when the GCD of m and I is equal to 1. That is to say, if I is coprime to m. How do we go about proving these for each of these different parts? How would we go about showing that? All right, so let's dive into it. So for the proof, we use the standard fact for an n cycle. Then pi to the I breaks into GCD of mi disjoint cycles. Each of length well, actually, okay, so yeah, each of length, well, use the standard fact for an m cycle. Okay, let's dial it back. Well, time-wise, let's go. No, those are lost seconds, but the orbit of any element under pi to the I is again an m cycle. If and only if GCD of m and I is equal to 1. So I have to put something else there, but if and only if GCD is equal to 1. So for part A, where m is equal to 12, sigma I is a 12 cycle. If and only if GCD of 12 and I is equal to 1. So I well, I corresponds to 1, 5, 7, 11, mod 12. and all integers congruent to these classes mod 12. That should be noted, right? Okay. And okay, let's go on to part B. That's satisfying. Okay, now part B here. Now that has m equal to 8. Sigma to the I is a 12 cycle. Sorry, 8 cycle. Well, what do we suppose that means? If and only if GCD 8 of 8 and I is equal to 1. So I corresponds to 1, 3, 5, 7 mod 8. And all integers congruent to these classes mod 8. Part C. M is equal to 14. So omega I is a 14 cycle. If and only if the GCD of 14 and I is equal to 1. So I corresponds to 1, 3, 5, 9, 11, 13 mod 14. And all integers congruent to these classes mod 14. Right. So this matches the general co-primality. Let's just, okay. No, you know what? Actually, yeah, why not? Why not? This matches the general co-primality criterion. Pi to the I is an M cycle if and only if the GCD of I and M is equal to 1. All right, let's move on to the next one, exercise 10. So let's work on exercise 10. So prove that if sigma is the M cycle, A1, A2, all the way up to the M cycle, open parentheses, A sub 1, A sub 2, all the way up to A sub M, close parentheses, then for all I within the set from 1 to all the way up to M, sigma to the I of A sub k is equal to A sub k plus I, where k plus I is interpreted modulo M as its least positive residue. Deduce that the order of sigma is equal to M. So intuitively, an M cycle advances indices by one step each application. Repeating I times advances by I steps, read modulo M, right? So this immediately implies that no power smaller than M can return every point, while the mth power does. So how would we say this more rigorously? Right, well, let's get into that. Oh, yeah, I can just do this kind of. If only there was there's like a, for, what is it, easy boards? Yeah, easy boards. Because it's magnetic, you just have like a slider that you can just put underneath it and erase everything just by going. Sometimes it doesn't work though, especially old ones. It takes a while, especially ones that have been like fatigued by pressure, let's say. So step 1, sigma to the power I of A sub k is equal to A sub k plus 1. Plus I for all I greater than or equal to 1. We argue by induction on I for I is equal to 1. This is the defining property. Assume sigma to the I of A sub k is equal to A sub k plus I for some I greater than or equal to 1. Then sigma I plus 1, sigma to the I plus 1 of A sub k is equal to sigma of sigma to the I of A sub k, which is equal to something I still have room for, which is sigma of A sub k plus I. And what is this equal to? That is equal to A sub k plus I plus 1. Again, with indices, reduced mod m. This completes the induction. And so we can proceed to step 2 after I erase the board. Okay, gotta bring us down to earth with this erasing the board thing every so often, yeah. God knows some math people are so far up their rears, right? But anyhow, let's just go on to step 2. Deduce order sigma to equal m. So from from step 1, with k is equal to 1, we have sigma to the I of A sub 1 to be equal to A sub 1 plus I. Now, if 1 is less than or equal to I, which is less than m, then A sub 1 plus I does not equal A sub 1. So, sigma to the I does not equal 1. On the other hand, for I is equal to m, we get omega to the m of A sub k, which is equal to A sub k plus m, which is equal to A sub k for every k. Did I define k to be anything? Let's see. Because I say for every k, but like, what is k, right? Let's just say k is, well, what is k? What is k? Crisis. Compiler error, right? K belongs to the positive integers. Yeah, so. Does it? Yeah, it does, because we have where k plus I is interpreted modulo m as its least positive residue. Plus I though, right? Plus I, so k could be, it wasn't my job to define k, it was their job to define k. Suffice to say, let's just say for every k, right? I guess what we could say is in the natural numbers, because that's just how it usually goes. Well, but then it's like, okay, k plus I, what is k plus I is interpreted modulo m as its least positive residue, which means 0. What about 0, right? So could k equal 0? Goodness gracious, what a crisis. Let me think about that. We get sigma m of that for every k. Let me think. Still not sure. I'm gonna say it's the natural numbers, but don't quote me on that. This is something, right? This is something to really look at. Goodness gracious. Okay, for every k, this is just sort of the indexing sort of thing, but so sigma m is equal to 1. Therefore, the order of sigma is exactly m. Let's see, would this work for, let me think, 0. Yeah, it should be the natural numbers, because we don't start from a naught, right? So, yeah, okay. Anyhow, the order of that is exactly m. Therefore, more generally, we can say sigma to the I of a sub k is equal to a sub k plus I, indices mod m, and the order of sigma is equal to m. Let's move on to the next problem, problem 11. So move on to exercise 11. So let's let sigma be equal to, open parentheses, 1, 2, on and on and on until we get to m, b, and m cycle. Bean. B and, not bean. Dang it. B and m cycle. So show that sigma to the power I is also an m cycle if and only if it's the GCD of I and m is equal to 1. So see, we don't really get to remember earlier we kind of just took that to be a standard thing. Well, now we actually have to shut up and show up, right? So we have to prove this thing. So think of sigma as a clock with m positions, right? Each application of sigma moves one tick forward. Applying sigma to the I means jumping I ticks each time. If I and m are relatively prime, then repeated jumps of I eventually visit every tick, one complete lap. Now, if I and m share a factor d greater than 1, then you only hit every dth tick, right? So breaking the cycle into d smaller loops. Now, how do we show that more rigorously, right? So check the camera, which looks good, and we'll go on to that. So for the proof, you have no proof, I have every proof. No, but for this proof, suppose sigma to the I is an m cycle. Let d equal the GCD of I and m. Write I is equal to dx and m is equal to dy. Then, open parentheses, sigma to the I, close parentheses, to the y, is equal to sigma to the I, y, which is equal to sigma to the d, x, y. That kind of looks like a derivative sort of thing, doesn't it? Well, anyway, open parentheses, sigma to the m, close parentheses, to the x, is equal to 1. Thus, the order of sigma to the I divides y is equal to m over d. But an m cycle must have order exactly m, hence m cycle. So m is less than or equal to m over d, forcing d is equal to 1. So that's the left-right implication way. Now let's go right-left. Conversely, assume GCD of I and m is equal to 1. Consider the orbit of m under sigma to the I. What we get is m maps to I asterisk. And we'll look at what that means in a bit. So open parentheses, 2i, close parentheses, to the asterisk, all the way to open parentheses, m minus 1, close parentheses, I, close parentheses, to the asterisk, all the way back to m. where I almost said K sharp whenever I first saw this, but it's K asterisk, K to the asterisk denotes the least, gosh dang it, positive residue of K modulo M. Now, because I has a multiplication, a multiplicative inverse, a multiplicative inverse modulo M, the numbers I, so the numbers I s to the asterisk and open parentheses 2I close parentheses to the asterisk, and we go on and on and on until we reach open parentheses M minus 1 close parentheses I close parentheses to the asterisk, are all distinct. All of these are distinct. Though, yes, okay. So, the orbit has size m, and sigma to the I is indeed an m cycle. Therefore, sigma to the I is an m cycle if and only if GCD of I and m is equal to 1. QED, man. Okay. All right. So then we go on to exercise 12. Check the camera, camera's good. Don't even have to rotate it this time. Now, a little bit of cross your fingers, but it's also just like, I locked the rotation, or at least kind of locked the rotation on the camera. So hopefully it stays to where like this perspective, like the upright perspective is what you have, and you don't have it like I had in this one video, 2 videos back on this sort of subject matter, where anytime I tried to upload it, just kind of stayed the course of erroring and preventing me from uploading the video after I had edited the rotation in there. So, these things happen, but don't like it. But anyway, c'est la vie. On to exercise 12. So 12 is broken into 2 parts, starting with A. If tau is equal to open parentheses 1, 2, close parentheses, open parentheses 3, 4, close parentheses, open parentheses 5, 6, close parentheses, open parentheses 7, 8, close parentheses, open parentheses 9, 10. Feel a bit more comfortable with that. Just sort of, I mean, you could still interpret that as 12, 34, 56, 78, 9, 10, right? But, so if this is the case, if tau is equal to this, right? So determine whether there is an n cycle sigma such that n is greater than or equal to 10, and an integer k with tau being equal to sigma to the k. So that's part A, that rhymes. So, and for B, if tau is equal to open parentheses 1, 2, close parentheses, open parentheses 3, 4, 5, determine whether there is an M cycle, an N cycle, sigma where n is greater than or equal to 5, and an integer k with tau equal to sigma k, sigma to the k. So intuitively, a power of n cycle is like, so walk k steps at a time around one big circle. When k and n share a common divisor that's greater than 1, the walk breaks the big circle into d equal smaller loops, right? So, which is an interesting way of looking at it. But each loop is a cycle of length n divided by d. This is reasonable. So to manufacture a given product of disjoint cycles, choose sigma so that every kth hop exactly lands on the desired pairs slash blocks, right? So how do we do that more rigorously? So let me just erase this. Start with A. So if let's take the 10 cycle. So we have sigma is equal to 1, 3, 5, 7. Oh no, that's a lot. Okay. So take this 10 cycle. We have sigma is equal to, open parentheses, 1, 3, 5, 7, 9, 2, 4, 6, 8, 10. Close parentheses. Compute sigma to power 5 to the fifth to 5. And what we have is, well, hopping 5 steps in this ordering. Swaps each odd with the following even. So sigma to power 5, let's see. So you could go into this step by step, but this would be equal to open parentheses 1, 2, close parentheses, open parentheses 3, 4, close parentheses, open parentheses 5, 6, close parentheses, open parentheses 7, 8, close parentheses, open parentheses, 9, 10, close parentheses, which is equal to tau. So tau is indeed a fifth power of an n cycle in which, and here n is equal to 10, right? So so let's sort of check that real quick. Check k equals 5 and n equals 10. So you could sort of see how you could construct this by going back, right? So give d is equal to, reverse engineering, I mean to say. Check k is equal to 5 and n is equal to 10. That's supposed to be a 10. Give d is equal to GCD of 5 and 10, which is equal to 5. So 10 cycle splits into 5 disjoint 2 cycles. Which is exactly what we wanted. K equaling 2. Sorry, wait. No. That's n, and then k is the finite number of these. So this case 5. Now let's go to part B. See what we can make of that. All right, so for part B, what do we have? Well, move this here. I can just sort of apply that to the corner, and it kind of works out. Kind of works out. Let me just kind of snap that this way. There we go. So for part B, the head of tau equals open parentheses 1, 2, close parentheses, open parentheses 3, 4, 5. Determine whether there is an n cycle sigma or n is greater than or equal to 5, and an integer k where tau is equal to sigma to the k. So to k. So let's suppose, right? Let's suppose tau is equal to open parentheses 1, 2, close parentheses, open parentheses 3, 4, 5, close parentheses. Gosh dang it. Where sigma to the k, I suppose t is equal to that. With, did I say sigma? Suppose tau is equal to sort of pair disjoint cycles where sigma k So it's like we're sigma k. So is sigma k for some n cycle with n being greater than or equal to 5. Gotta blow my nose. All right. So if n is greater than 5, then sigma to k must fix every point 6, 7, all the way up to n. But a power of an n cycle either fixes every point when it's the identity, for instance, or fixes no point. Outside its orbit structure. Hence, sigma to the k cannot have those fixed points unless sigma to the k is equal to 1, contradicting tau is equal to 1. Therefore, n is equal to 5. Now, we don't have a lot of room here, so I'll erase this, and then it's supposed to be tau, not tau. Okay. So now n is equal to 5 is prime. For a 5 cycle, sigma to the k is a 5 cycle if and only if GCD k of k and 5 is equal to 1 and is the identity if and only if 5 divides k. In either case, sigma to k cannot, just realize how interesting it is. 2 to the power 5. Just realize we say 2 to the power 5, right? I mean, that's an interesting thing because we say like mappings that way, and we also say like cycles, but that's an interesting thing, right? I mean, it's its own sort of function. So yeah, that kind of makes sense in a way. Second, I'm about to sneeze, I think. Goodness. In either case, sigma to k cannot equal a product of a 2-cycle and a 3-cycle. Therefore, no such sigma k exist. Yeah, okay. Just trying to check if anywhere I made a mistake. I'm still looking. Or if Kikola did, right? So, but I'll take the blame on me since I typed up the notes. Don't think I did anything wrong. I have some... Don't think so. I don't think so. I don't think so. Maybe though. So if I did something wrong, please correct me. And on to 13. Now, exercise 13, for that we have show that a permutation sigma of S sub n has order 2 if and only if its cycle decomposition is a product of disjoint two cycles and at least one two cycle appears. So show that a permutation of sigma sigma in the symmetric group S sub n has order 2 if and only if its cycle decomposition is a product of disjoint two cycles and at least one two cycle appears. So equivalently, every moved point lies in a transposition and sigma is not equal to 1. Intuition. So an involution is a pairwise flip, right? So squaring a transposition gives the identity, and a disjoint transposition okay. So squaring a transposition gives the identity, and disjoint transpositions don't interfere. If there are no flips at all, you get the identity whose order is 1. So let's look at that idea a bit more rigorously. So this is an if and only if, so let's start with the left-right. The left-right, You know, it's funny. In English, if you look at that, well, if you were to read that right-left, you'd see right-left, but we read it so in English, that's left-right, but anyway. So the left-right implication, if sigma squared is equal to 1 and sigma does not equal 1, then any moved I satisfies sigma of I, which is equal to j, and sigma of j is equal to I. So open parentheses I, j, that cycle, occurs in the decomposition. No cycle of length There we go. Of length. All of my ingrained habits automatically took me over with writing length. Gosh dang it. So no cycle length. I say it and then I immediately do it again. Greater than or equal to 3 can occur. A T cycle with T greater than or equal to 3, well, doth not square to 1. Does not square to 1. Hence, so every non-trivial cycle is a 2 cycle, and the cycles are disjoint. Therefore, sigma is a non-trivial product of disjoint 2 cycles. Which is what we wanted. I guess that's kind of why I was just thinking about this. Why not tau equal to 1 in the previous case? Well, it's like, well, you don't just want to consider the trivial case, right? But I didn't see anything inherent within the question itself that said that that couldn't be so. I just sort of assumed it wasn't the case, but anyhow, let's move on to the right-left implication. So, for the right-left implication, we assume, say, if sigma is equal to, open parentheses, a sub 1, b sub 1, this is just an underscore. Don't even need it for this one because, well, I mean, you clump them together, so what? You have that sub 1 to offset it. A sub 1, b sub 1, all the way up to, open parentheses, a sub k, b sub k, close parentheses, is a product of disjoint 2 cycles then, open parentheses, a sub r, b sub r, close parentheses, squared is equal to 1, and the factors commute. So, sigma squared is equal to 1. If k is greater than or equal to 1, i.e., well, that is at least 1 2 cycle appears. then sigma does not equal 1. Hence, the order of sigma is equal to 2. Now, if k equals 0, no 2 cycles, right, then sigma is equal to 1, and the order of sigma is equal to 1. So therefore, sigma, and this is like to combine both of these points, has both implications, has order 2 if and only if it is a non-trivial product of 2 disjoint cycles. Oh, sorry, of disjoint 2 cycles, sorry. Now, equivalently, right, from earlier, equivalently, sigma is equal to 1 exactly when no 2 cycles appear. On to 14. Do we have time? Let's just save it for the next one, because this one is rather long, and I want to be able to not be too rushed on it. You know, rushed enough because, you know, finite time and mortality are a thing, but not so rushed as to just kind of go a little too fast. And, you know, you'll know it when you see it, right? That sort of thing. But, yeah, so we'll continue on in the next one.